MS Ramaya University of Applied Sciences.
Hi students, let us discuss fundamentals of structural geology. We know that rocks play a vital role in civil engineering applications. The strength of the rock is governed by the mineral constituents as well as textural arrangements, and the rocks need to be strong for the civil engineering structures to remain stable. Yet, the so-called sound rocks may turn out to be weak when they are subjected to stress inside the earth. Stress is conventionally defined as a force per unit area as shown in figure. The forces acting on the rocks are of two types. They are lithostatic stress and differential stress. Lithostatic stress is an uniform stress that operates equally in all directions in rocks. Rock beneath the Earth's surface experiences equal pressure exerted on it from all directions. Differential stress results from compressional or tensional tectonic stresses that are not equal from all directions. Differential stress is directional in nature. The directional stresses may be tensional, compressional, or shearing and are termed accordingly as tensional stress, compressional stress, and shearing stress. Compressional stress tends to decrease the volume of rock material, giving rise to a unique geological structure called folds. Tensional stress induces stretching, resulting in the development of fractures in the rock, and the resulting geological deformational structure is a fault. Shearing stress results in slippage and translation, giving rise to transform faults. At the Earth's interior, the crustal rocks experience unequal stress due to the tectonic movement of crustal plates, and many unique deformational structures are formed in the process. They are folds, faults, and joints. In civil engineering terminology, the deformational structures are termed discontinuities. The discontinuities influence the bearing strength of the rock. The geological structures that are of civil engineering importance are folds, faults, joints, and bedding. Here we describe folds and faults. Folds are defined as the undulations in the rocks formed due to compressional stress. Geometry of the fold. Axis. A line drawn along the points of maximum curvature of a layer of a fold. Axial plane. An imaginary plane surface that divides a fold as symmetrically as possible. Limb. The two sides of a fold are called limbs. Plunge. If the fold axis is not horizontal, the angle of the axis with the horizontal plane is called plunge. Depending on the type of fold, the structure will have crest and trough. Folds are of various types. In civil engineering, the anticlinal fold, synclinal fold, monocline and isoclinal folds are of greater relevance. Characteristics of an anticlinal fold. Arching of rock layers, youngest formation at the crust, limbs dip away from each other. Characteristics of an synclinal fold. U-shaped fold or a downward flexure, youngest rock formation at the trough. Limbs dip towards each other. Monocline is nothing but a gently tilted rock formation. Anticlinorium is a broad, regional anticlinal folded structure in which the limbs comprise minor folds and flexures. Isoclinal folds show folding with their limbs lying more or less parallel. Overturned fold and recumbent folds are very pronounced isoclinal folds with their fold axis inclined in the same direction but differ in their dip angle. Recumbent fold has its fold axis aligned nearly horizontal. Fault. A fault is a planar fracture in a volume of rock across which there has been significant displacement parallel to the fracture. Geometry of the fault. Fault plane is the plane that represents the fracture surface of a fault. Fault line is line of intersection of the fault plane with the ground surface. It is also called trace of the fault. Slip is defined as the relative movement of geological features present on either side of a fault plane. The vertical component of the dip separation is called the throw of the fault. The component of horizontal represents the heave. Types of fault. Basically, two types of fault are common. They are dip-slip and strike-slip faults. Dip-slip faults are again classified into normal fault, reverse fault. Normal fault results when the hanging wall block moves down with respect to the footwall block. Reverse fault results when the hanging wall block moves up with respect to the footwall block. Horst and graben are block faulting features associated with normal faults. Horst represents a block pushed upward by the faulting, and graben is a block that has dropped due to faulting. Strike-slip fault results when the offset is predominantly horizontal, parallel to the fault trace. Strike-slip faults are due to shearing stress. Strike and dip. The structural features are recorded in terms of dip and strike. Strike refers to the direction of the line of intersection of the dipping bed with the horizontal plane. Strike is expressed as a bearing from true north. Dip refers to the inclination of beds with respect to a horizontal plane and is measured in degrees. While recording dip, the direction as well as the amount of inclination are both important. Dip may be true or apparent. The maximum inclination is termed true dip. Apparent dip appears in a vertical plane but not exactly perpendicular to the strike. When strike and dip are expressed together, the data is called as attitude. Attitude is measured with the help of Brunton compass. Brunton compass. In the compass needle points towards the magnetic north pole. The compass has an adjustment for the magnetic declination value for a given geological region. The strike of the rock formation or a bed is read with respect to north, generally read on a quadrant dial. For example, north 25 degrees east, south 25 degrees west, otherwise 025 and 215 azimuth. If the dip is 0, then the bed is horizontal. If the dip is 90 degrees, then the bed is considered vertical. Dip is perpendicular to the strike anywhere between vertical and horizontal. In the field, dip may be read as true dip or apparent dip. The maximum inclination is termed true dip. Apparent dip appear in a vertical plane but not exactly perpendicular to the strike. The attitude of various geological structures are measured in the field and plotted on the geological map. This geological map with the attitude marked enables to draw a geological cross-section. The geological cross-section helps largely in planning and designing a stable civil engineering structure.
Hello everyone. Today let me introduce you all to the fundamentals of structural geology. We know that rocks play a vital role in civil engineering applications. For a civil engineering structure to remain stable, the rock need to be very strong and sound. The strength of the rock depends mainly on the mineral constituent present in them and the textural arrangements of the minerals. Even if the rock, which is apparently very strong, when gets subjected to certain deformational stress, the rock tends to develop certain weak planes. These weak planes affect the stability of the engineering structures. Now we talk about stress. Stress that acts on the rock types. Okay. Now, there are stress is defined as the force per unit area, and stress is mainly of two types. Number one, lithostatic stress and differential stress. Stress is broadly classified into two types. One is lithostatic stress, other one is differential stress. Lithostatic stress is a stress that acts uniformly or equally in all directions on a rock. This generally takes place beneath the earth's surface. Differential stress is directional in nature. The directional stress is classified into three types, namely compressional stress, tensional stress, and shearing stress. The compressional stress gives rise to sort of unique geological structure called as folds. Generally, a horizontal bed when it gets compressed, it develops undulations, and such structures are called as folds. The tensional forces or tensional stress causes in general the slippage of beds. Is a slip plane, slippage of beds, generally in the direction of the dip. On the other hand, the shearing stress induces slippage and is translational in nature, and this takes place along the plane, on the horizontal plane. And a classic example of this shear stress induced translational fault is the San Andreas fault in California. Now we discuss about the folded structures. Folds are nothing but, as said before, there are undulations in a rock developed due to compressional forces. Folds can be classified into anticlinal fold, synclinal fold, monoclines, anticlinoriums, and isoclinal folds. Anticline. This is an anticlinal structure. This is a symmetrical anticline and this is an asymmetrical anticline. Here it contains limbs with reference to the axis of the fold. These limbs dip away from the axis of the fold, that is away from each other, and this is having a crest here, and invariably the younger rocks are seen at the crest of the fold. This is the oldest rock. Next one is the younger to the red one. Next is younger, the youngest. And youngest rock is always at the crest of the anticlinal structure. The other type of fold is the synclinal fold. Synclinal fold is a U-shaped fold in contrast to the anticlinal fold, which is arcing type. Here, this is a symmetrical syncline. This is a symmetrical syncline because the limbs dipping towards each other in a symmetrical fashion with reference to the axis of the fold. Here, in synclinal structure, always the younger rock type. All these color bands indicate different rock types or different ages, starting from the oldest at the bottom and youngest at the top. The youngest rock is always in at the trough of the synclinal structure. Monocline. The term monocline refers to a gently tilting rock formation. The tilting results due to, again, the tectonic forces acting on the beds. Anticlinorium. Anticlinum is a very broad and very regional geological structure. It is basically a anticlinum, very broad anticlinal structure with the limbs developing fractures in them. Generally, it is of a very huge dimension in comparison to anticlines and synclines. Isoclinal folds are folds having limbs that are aligned more or less parallel to each other like this, with reference to the axis of the fold. Some of the isoclinal folds are overturned and recumbent. These folds result when the fold axis is almost nearly horizontal, and such folds are termed as recumbent folds. Now we talk about faults. Fault is a planar fracture developed in a rock across which significant displacement of beds have taken place. This bed has moved with respect to the other block. This is called as the fault. Such a structure, such a deformation structure developed due to the tensile forces acting on the rock inside the earth. In order to describe the fault, we need to understand the geometry. This is the axis of the fault. Axis means is a line along which the displacement has taken place. This is the axis of the fault. And here there will be a vertical displacement from here to here. This is described as throw of the fault. Along with this throw, there will be a horizontal displacement to this distance. This is called as the heave of the fault. Let us talk about faults. Faults are basically classified into two types depending on the direction of movement. One is the dip-slip fault and other one is the strike-slip fault, depending on the direction of the movement of beds. One is the dip-slip fault, and other one is the strike-slip fault. This is the alignment of beds and the movement has taken place parallel to the direction of alignment of the rock types. Or the dip-slip faults are classified into two types: normal fault and the reverse fault. Now, in a fault, there are two blocks. One block is called as the footwall, other one is called as the hanging wall. In a normal fault, the hanging wall generally moves down or slips down with reference to the footwall. This is a normal fault. In the reverse fault, generally, there is a footwall, there is a hanging wall, and the hanging wall is moved, or hanging wall moves up with reference to the footwall. This is called as the reverse fault. This is the normal. Associated with normal faults are another unique type of faults. They are called as the horst and graben. Horst are the faulted blocks that have been moved up with reference to the normal fault on either side. The graben, on the other hand, is a block representing downward movement of the block with reference to the normal fault on either side. This graben is a depression generally. The classic example is the Narmada Tapti lineament in India is a classic example of the graben type of faulting. In contrast to the dip-slip faults, the strike-slip faults on the other hand, they show movement horizontally with reference to the fault trace along the direction of the beds. Now we discuss about strike and dip. Now all the geological structures, maybe faults, folds and the bedding characteristics etc. are described in terms of strike and dip. What is strike? Strike is nothing but a direction of the line of intersection between the horizontal plane and the inclined plane, and this line is supposed to be the line. This line is supposed to be the strike of the bed. Strike is always measured with reference to the north. Now the dip. Now dip refers to the angle, the inclination of the bed with reference to the horizontal plane. With reference to the horizontal plane. Now dip is always measured in degrees. Dip has got both amount and direction, whereas strike is only directional in nature. Dip may be true dip or apparent dip. The difference between the two is that true dip is always perpendicular to the strike direction and it represents the maximum inclination, whereas apparent dip need not be truly perpendicular to the strike direction. Geologists term the strike and dip components put together as attitude of beds. The strike and dip or the attitude is measured in the field with an instrument called as Brenton compass. The Brenton compass, like any other compass, has a needle pointing towards the magnetic north pole, and the compass also has an adjustment for the magnetic declination value for a given geographic region. And the strike of the rock formation or a bed is read with respect to the general north on either a quadrant dial or a azimuth dial. Here this compass represents azimuth values. The strike of the bed is measured with a Brenton compass by aligning the compass parallel to the rock formation and placed horizontally and is read in terms of north. In this case, it is north, 25 west, so 25 east in the quadrant scale, or it is 335 degrees in the azimuth scale. Once we measure the strike, we need to measure the dip. Dip, as told before, is the amount of inclination of the bed. Here, the beds are dipping fairly steeply and it is measured as 45 degrees with the help of a vernier scale provided in the compass. If the dip measured with a Brenton compass is read as 0 degrees, that indicates very clearly that the beds are not inclined but are aligned in the horizontal fashion. I am showing this and going to show the map to you now. Here is a geological map where the beds are read as 0 degrees with respect to the alignment. The 0 degree dip represents that the beds are horizontally aligned, as I have already told you. Here in this map, the solid lines do represent the geological boundaries, that is the contact between different rock types, and these disconnected lines, they represent the contours, the topographic contours with having a particular elevation values. Now here you can see these geological boundaries are not crossing with the contour lines. That means the beds are aligned horizontally with respect to the contours, and it is the horizontal beds or the horizontal dipping beds are represented the symbol plus, as shown here. On the other hand, if the beds are shown dipping 90 degrees, that means they tend to be vertical in nature. Generally, the beds invariably range between 0 to 90 degrees. In this geological map, there are many features. Here, this shows different rock types represented by different symbols or hatches, and there are certain markings over these beds, individual beds. One is the slightly longer line, and another one shorter segment perpendicular to that one. So this represents, as I told you, the strike and dip of the individual rock types. The longer segment is the strike, and the shorter segment perpendicular to the longer segment is the dip. They got a direction and amount. Here in this map, this particular bed showing the dotted symbol is aligned in direction northeast and southwest, and the dip direction is towards southeast with an inclination of 50 degrees. This is how the inclined beds are represented on the map. Here, generally, while reading from the Benton compass, the individual beds having different varying amounts of the inclination. There, the maximum amount or the maximum inclination is taken as a true dip, and the remaining ones are the apparent dips. And true dips are invariably perpendicular to the strike direction. In this map, now, here what are the features that we can find out? Besides the strike and dip, we know the geological boundaries marked here, and there will be this closure of the formation represents the folding characteristic. Here, the dip direction they are away from each other on both sides of this particular feature. That means it shows an anticlinal axis. That means the limbs of the structure, they are dipping away from each other. The central line that can be drawn here is the axis of folding, and that is represented as a line with a triangle showing the dip directions or the inclined direction. And beside this folded structure that can be identified as anticline, there is one more solid line here where different belts are truncating against another formation. You can see this formation is not continuous, it is abruptly ending against this particular line. This is the fault. Now we have described the fold and fault. As you know, here is a fault structure, is a folded structure. And coming to the cross section, with the help of the strike and dip data and the rock details, we can draw the cross section on different scales. This is the geological cross section, that is the subsurface characteristics of the rock formation that show the anticlinal structure with the limbs of particular rock dipping or inclined away from each other with reference to the central axis of the fold, and this limb is truncating against line called as the fault line, where different rock type is positioned adjacent to the rock type in this particular segment. So this is a fault. These features are very important in designing the civil engineering structure or major civil engineering structures of a given project. So this completes our experiment on the understanding of the geological structures in the context of civil engineering.
At MSR UAS, we spark your imagination unlike any other.